Comet 3 I/Atlas, captured in a remarkable observation using the Gemini Multi-Object Spectrograph (GMOS) on the Gemini South Telescope at Cerro Pachón in Chile on August 27, 2025, has quickly drawn the attention of astronomers around the world. The image, produced with the combined efforts of the International Gemini Observatory (NOR Lab), the National Science Foundation (AURA), and the Shadow the Scientist program, showcases the comet with exceptional clarity. Thanks to the detailed image processing completed by J. Miller, M. Rodriguez, T. Rector, and M. Zamani, even the subtle textures of the comet's coma and the fine structure of its tail have been brought to light. These observations, which are part of the NOIR Lab Educational Observing Program, reveal a fully active and unmistakably natural comet displaying all the classic features associated with such icy wanderers from the far reaches of the cosmos. What makes 3 I/Atlas particularly fascinating is not simply its brightness or its interstellar origin, but the clarity with which its cometary activity can be observed. When astronomers study objects entering the inner solar system, they rely on several key signs to determine whether the object is a comet or an asteroid. In the case of 3 I/Atlas, the presence of a bright coma surrounding the nucleus and a long, continuous tail extending outward are definitive indicators of a true comet. These features are not caused by imaging errors, reflections, or sensor noise. Instead, they are physical manifestations of material escaping from the comet's icy nucleus as it warms under the sun's increasing influence. Comets are made up of volatile substances such as water ice, carbon dioxide, carbon monoxide, methane, ammonia, and a variety of organic compounds. When a comet approaches the sun, these ices begin to sublimate, a physical transformation in which solid ice turns directly into gas without passing through a liquid phase. As this happens, the gases escaping from the surface drag tiny dust particles with them, forming the cloud-like coma that envelopes the solid nucleus. Solar radiation and charged particles streaming from the sun then push this material outward, forming the tail that can stretch across millions of kilometers of empty space. Every part of this process is visible in the case of 3 I/Atlas, confirming that it is behaving exactly as a natural comet should. The distinction between a comet and an asteroid becomes obvious when examining their physical behavior. Asteroids, which are mostly composed of rock and metal, lack significant volatile materials. They do not produce comas or tails because their surfaces remain solid and inactive, even when exposed to the sun's heat. Their motion through space is typically predictable, driven solely by the gravitational forces acting upon them. In contrast, 3 I/Atlas shows all the hallmarks of sublimation-driven activity. Its glowing appearance, dusty halo, and extended tail are signatures that no asteroid could mimic. Because 3 I/Atlas arrived in our solar system from interstellar space, it quickly became a subject of public speculation. Some observers have wondered whether unusual interstellar objects could be artificial, perhaps sent by distant civilizations for exploration. While the idea is imaginative, the behavior of 3 I/Atlas strongly contradicts any artificial origin. If this were a spacecraft or probe, scientists would expect to see precise movements, course adjustments, or deliberate changes in velocity, behaviors associated with controlled propulsion. Instead, 3 I/Atlas follows a simple hyperbolic trajectory shaped only by gravity and the natural forces of outgassing. It neither slows down nor accelerates in any way inconsistent with the physics of comets. An artificial object would also appear visually distinct. It would not hide behind a cloud of gas and dust because manufactured materials like metal or composites do not sublimate into vapor when exposed to sunlight. A spacecraft would reveal sharp edges, reflective surfaces, and clear structural patterns. But the images of 3 I/Atlas show no such features. Its nucleus is obscured within its coma, its brightness is diffuse rather than concentrated, and its overall profile lacks any symmetry or engineered design. Instead, it resembles every natural comet previously observed, from texture to color to spectral signature. Spectroscopic studies reinforce this conclusion. When scientists examine the light coming from the comet, they detect the presence of water vapor, carbon monoxide, hydrogen cyanide, and dust particles typical of cometary compositions. These elements and compounds are commonly found in primordial solar system bodies and match the profiles of comets studied over several decades. No metallic signatures, artificial alloys, or engineered chemicals appear in the data. Only natural ices and dust grains that have existed since the birth of other stars. The tail of the comet, too, behaves exactly as expected. Solar radiation pushes the dust tail away from the sun, while charged particles from the solar wind create a secondary ion tail, faint but measurable. These physical interactions are well understood, and they form specific patterns depending on the composition and speed of the comet. In every respect, 3I/Atlas follows known cometary behavior. Its tail is soft rather than sharply defined, its particle distribution matches sublimation models, and its brightness changes as it approaches and recedes from the sun, all characteristics of natural objects. Its motion through space offers further evidence. 3I/Atlas follows a hyperbolic orbit, meaning it is not bound to the sun and will eventually leave the solar system forever. Natural interstellar comets behave this way because they drift through the galaxy on long, unpredictable trajectories after being gravitationally ejected from their original planetary systems. If an artificial probe had entered the solar system, it would behave very differently. It would not simply coast past without slowing or attempting to study planets. It would not waste fuel by performing no maneuvers. Instead, intelligent design would likely involve purposeful movement or orbital insertion around a body of interest. Because 3I/Atlas is an interstellar object, it provides scientists with an extraordinary opportunity. Comets from beyond our solar system carry material formed around other stars, something astronomers rarely get to study. By analyzing the gases and dust released by the comet, researchers can learn about the chemistry of distant planetary systems, gaining insight into how planets form and what ingredients might exist on worlds far from our own. These interstellar messengers act like cosmic time capsules, preserving ancient ices and chemical compounds from their home systems for billions of years. As 3I/Atlas travels through the inner solar system, it sheds layers of material that have remained unchanged since the formation of its home star. These materials may include organic molecules, silicate grains, metals, and complex carbon-based compounds that could offer clues about the building blocks of life elsewhere in the galaxy. Scientists study these details not only to understand the comet itself, but to grasp the broader picture of how planetary systems evolve and what makes each star system unique. Ultimately, every piece of evidence, from appearance to composition to orbital behavior, confirms that Comet 3I/Atlas is a completely natural interstellar comet. It shows no signs of artificial origin, no unusual maneuvers, and no anomalies that suggest anything beyond standard comet physics. Its coma and tail, its motion, its spectrum, and its structure all fall perfectly within the expected behavior of icy bodies responding to the sun's heat. Rather than being mysterious or artificial, 3I/Atlas is a beautiful example of natural cosmic processes at work. It is a visitor from another star, a frozen relic traveling through our solar system for only a brief moment before returning to the vast interstellar spaces from which it came. Its presence gives astronomers a rare chance to study material untouched for eons and to deepen our understanding of the galaxy's countless planetary systems.